All right, guys, we're going to start with a warm-up question from yesterday where we were talking about those quadratic applications. There is one on your test coming up next week that looks just like this. This one has a bit of weird wording. I think we copy and pasted from another problem and the wording doesn't make sense, but we'll figure it out. So these charts are just giving you an opportunity to kind of figure out what numbers you're working with some concrete examples. And then your job is to eventually express this algebraically so you could find the maximization point, which is fancy talk for graph the parabola and find the max. So Sari is making sales calls to 12 stores. So let's put that in the chart. If she visits 12 stores, then I'm hiding the information. This is not anywhere on your paper, guys. It's just a warm-up problem. I don't know. She sells 60 boxes every store, if that's what she's doing. So total number of boxes, mathematically, we realized we'd have to multiply these together. And we're going to get 720 boxes. Now, the actual number here is going to help me figure out my window in a minute. And it's also going to help me kind of realize the calculation, which isn't really going to be that shocking because hasn't it always been this times this for these charts? Like every example we had yesterday was this times this. So big shock, I know. So then there's an additional clue here. It says if she makes an additional sales call, then the number of boxes she sells decreases by 3 per store. Oh, never mind. I lied. The wording's fine on here. All right. So if she makes an additional, sales call is what it's supposed to say. Whatever. Okay. 13. What happens to her number of boxes? It goes down by 3, so down to 57. Good. So this I need a little calculator help on. What is 13 times 57? 748? 41 makes more sense because 7 times 3 is 21. Okay, 741. So we could continue on with the examples of what's really going to happen in real life, but instead your teacher wants you to come up with some algebra. So how could you express this column knowing that we start at 12 and then we move down in such a fashion? What would that look like for algebra?
X plus 1.
12 plus x. There we go. And then this column, you start at 60, but how do we move down the column?
Minus 3x.
Very nice. And then we already know that we're supposed to multiply these together, and that's going to produce whatever this answer is supposed to be. So what we're going to do now is we're going to move to our calculator. And we're going to go to Y1, and we're going to type in exactly this. We're not going to simplify it. My calculator's cool. It doesn't matter if I simplify. 12 plus x quantity times 60 minus 3x. I'm going to pause the video while I get this all adjusted, and then we'll talk about window creation in a moment. So once you have your function typed in, sometimes you luck out, and if you hit graph, maybe the last question you did had a good window. That's not a good window. That's a standard window. All right, so let's go to the window, and let's think about what x represents in this question. This question represents a few things if you look back at the chart here. It's how many extra stores she's visiting, and then also in this part of the equation, it's removing 3 x's in groups. So if I think about like how many I could remove to the point where I have nothing left, wouldn't like 20 be a good ending point there? Because 3 times 20 would be 60 minus 60. So that would be the end. So going back to my, where'd you go? Going back to my calculator, 0 seems like a good place to start. And I surely won't be able to go any bigger than 20 because we'd have nothing left. Now, yes.
Happy birthday.
Thank you. Then we could try Zoom Fit. Sometimes it works, sometimes it doesn't. But the other thing I noticed is in my chart, remember your numbers were like 720 and then we get a 741. So they're kind of hovering like mid 7s right now. So I'm thinking I can just manually adjust the y's that way. I don't really care where you start your y's. 0 is fine. But I'm going to go up to 800. I feel like that's a safe place to end. And then I'm going to hit graph. Oh, that's beautiful. Because what I need from you is the maximum of that parabola. So, second trace, very good. Maximum. And then I like to hop around because I'm too impatient to scroll. So, remember my window, I forgot what it was doing. Going to 20, wasn't it? So, if I need to come way over here, I'm going to go like 2. Definitely to the left of the max. That was a little close, my bad. All right, 10 is definitely to the right of it. All right, so the ordered pair that we jot down, which is important, is 4, 768. So now we're still not done because we just found a max at 4, 768. Now you have to know what this maximum means. I know this is what x represents. this is actually the total boxes, right? That's what it's representing. So it would have had one of these charts. Boxes would have been 768. A lot of kids get to this point and then they write down 4 and then they walk away from the question and they get it wrong. Why are they getting it wrong? Because the question says, find the number of stores. Thank you. Find the number of stores that she should go to. So go to your number of stores expression. I know x equals 4, but that means she's supposed to visit 16 stores. So that really breaks my heart when kids get to that point of the question because they did all that hard work. And then they're like, 4. It's not what they want. Okay, so read carefully. It's just like that on the test too. This is gibberish. Ignore this, ignore this, ignore this. All right, here's the beginning of our lesson. So we're finally in chapter 1. We're going to start off with a pretty gigantic subject called functions. Yeah. But the good news is a lot of this stuff is, like, you've talked about it quite a bit in Algebra 2. So this diagram, which is the same as this diagram, is explaining to you the order of numbers. So this is not really crucial to your development in PreCalc, but just so we're all on the same page here. When you are little teeny babies, you start learning about what's called the natural numbers. That's when you start counting on your fingers, 1, 2, 3, 4, 5, and so on. And then as kids start to get a little older, they understand the concept of nothing. So then they teach them the number 0. And then if you ever talk to a little kid about numbers, they're pretty certain that 0 is the tiniest thing you could ever have, right? They're like, well, it's 0. There's nothing more. So those are called, that's the whole number system. So 0, 1, 2, 3, 4, 5 is whole numbers. And then we really blow their minds in about 2nd grade and we say, did you know your numbers can go negative? I'm like, what? So that encounters the concept of integers now. So they still look like whole numbers, but now you can go negatively on the number line as well. And then we really mess with them in 3rd and 4th grade and say, oh, you can write things as fractions. So like forget the numbers 1, 2, 3. There's a whole bunch of numbers in between 1 and 2. And then we start breaking up things in what's called a rational number system. So the rational number system is over-encompassing all of these other guys. So like the number 2 is a natural, a whole, an integer, and a rational number. It's all of them. Okay. Because can you write 2 as a fraction? Yeah. 4 over 2, 2 over 1, 6 over 3. So anything that could be written as a fraction is considered rational. And then this really messes with kids. You ever talk to a little kid about Pi Day? And a little plug out there. That new movie, Wonder Park, or whatever it's called, do I have the right name? You guys don't watch cartoons anymore because you're not children. But they have a Pi song in there because the kids go to math camp. And I, as a birthday request, want you all to learn it tonight and come back and sing it to me because I had tears in my eyes when I heard this. Okay, homework. In addition to your 10 homework problems. Alright, so pi, irrational. Like, they're like, what's pi? 3.14159, blah, 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 blah. You know, it never ends. You can't write it as a fraction. It's just a weird number. Square root of 2, other weird number. Alright, so here's technically a new thing for you that we actually aren't going to use. Your book introduces you guys to what's called set builder notation. I'm going to show you what it looks like, and then we're all going to agree that it stinks and we don't want to use it. Okay? We, however, love, here at Harlem, we love interval notation. Interval notation is that stuff with the infinities and the brackets and the parentheses. So I'm going to ask you guys to remember some things about interval notation, and you did a ton of this in Algebra 2. So should come to you a little quicker than some of the other things that has been, like, when I asked you guys to remember distance formula a while back, and you're like, yeah, it's been like 3 years. Not for this, right? You just got done using interval notation in Algebra 2, or whatever course you did recently, okay? You hated it. Well, this will be the moment that you love it. Ready? This is what you should hate, dear. This is set builder notation. Look at this. Okay, can I translate this for you? So let's say the set of all numbers x, and then they put a line right here, which means such that, because that's what I think a line would mean. So such that all of your x's are between the values of -3 and 16 inclusive, meaning they count -3 and 16, where x is an element of the real number system. Yes, that seems logical. You want to start writing your solutions that way? Me neither. Plus you got to make these weird squiggly brackets. Remember these guys? No one likes set builder notation. We're not going to do it. Forget set builder notation. This is what you guys are going to have to do for me. Interval notation. What does this interval mean? your solutions start at 18, and they continue on forever. So there's no way we could list out all of our solutions, because it literally is an infinite list. The fact that 18 has a parenthesis on it, what does that mean to you? Like, does 18 count? No. 18 doesn't work, but everything after 18 works. So, like, for instance, 18.0001, totally good solution. Not 18. All right. Let's do some examples here, guys. Skip this. Here. Now, dyslexic teacher over here. To this day, and I'm old now, I still have to really focus and concentrate on what the symbol means. Can someone read this symbol to me? It is a less than or equal to symbol. And how do you remember that that is a less than symbol? Oh, did you just pull an alligator out at me? Oh, no alligators, child. Okay, you can't use alligators on variables, guys, because you don't know what they are. Ugh, jeez. All right. How do I know that's a less than? No one has a trick for that? You're just really smart and good at this? Okay. Well, I need a trick because I'm dyslexic. It looks like an L. Potato, potato, man. It looks like an L.
Where's the L? Oh.
Boom, L. And I'm going to be honest. I'm still one of those people, like, once in a while in my life, I got to hold my hands up and make my L's to know which hand is left. I'm sorry. I have dyslexia, man. So, do you know how many times I've read an inequality symbol wrong? A lot. I cost my math team partner a medal at state because I read an inequality symbol wrong. Dang it.
Wow. Was he mad?
He was mad. Yeah. Sorry, Josh. Okay.
You told him what you messed up?
Oh, he knew.
Oh.
It was a team event, and I was like, less than, and then we came back, and he was like, that was greater than. You're fired. All right. I need to graph this. I just need to. Maybe you don't have to. I do. -2. Throw it in the middle of the number line. And you guys told me less than -2, so which direction would I be shading all my solutions on the number line? It'd be this way. And on the actual -2 itself, would I be using a parenthesis or a squared off bracket? Why is it a squared off bracket? Because it has an equal to symbol, which means -2 is included in your solution. So now, the reason I like to graph them is because I can read the interval very easily now from left to right, because that's how we read things in America, I guess, and most places. Left to right, starting at, good, negative infinity lives out there, and then it ends at -2 with a bracket. What happens when you, whoopsies, reverse your interval? You're wrong. We learned that the hard way in Algebra 2, didn't we? What happens if you think infinity has a bracket on it? You're wrong, because infinity always has a parenthesis. Anyone want to elaborate why infinity always has a parenthesis?
Oh, because you can't include infinity.
Right. That's so silly. Like, show me infinity.
Yeah, you can't do it.
Infinity's a concept, man. It's not a number. Yeah, this is a fight. A lot of kids have this fight with each other when you're little, right? Like, I hate you infinity, I hate you infinity plus 1. Yeah, you heard that before? Yeah, that's stupid. Doesn't mean anything. You're stupid. Yeah, bring that out to a small child. You're dumb. Yeah, don't say that to kids. They don't like that. So negative infinity is a conceptualization of going on forever. It's not actually a place you can land, therefore you can't put a bracket on it, right? Infinity, same idea. You can't get there, so you got to use parentheses. Let's talk about this guy. Negative x is greater than, I'm assuming, because it doesn't look like an L, greater than -8.8. So if you wanted a number line, you could throw one down. Talk to me about whether 8.8 has a bracket or parenthesis on it, though. -8.8? Does it have a bracket or parenthesis? Parenthesis. All right, and I'm going greater than him. So a parenthesis this time, because it is not equal to -8.8. It doesn't have that equal to piece. So starting on the left and working your way right, your interval starts at -8.8 and then continues on until forever. Are you getting better at drawing infinity symbols?
No.
Nope. Well, if you have to, just turn your paper 90 degrees, draw an 8, and turn it back. Or you can just draw 2 zeros next to each other. Does that work?
Yeah.
Yeah. All right. This one. These are called, I call them sandwich inequalities. The solution, the variable is sandwiched between two solution sides. So can you guys interpret this for me? This one everyone can read. That's an x is less than 15. But what does this one say? Yeah, it really says x is greater than 5. So you're supposed to be graphing all solutions that are both greater than 5 and less than 15. So the way that looks on a graph is, we call these and problems. Remember these ands? And it's going to be all my numbers that are greater than 5 and less than 15. Notice I used parentheses on both because there's no equal to symbols on either one of those. So we don't include the endpoints. This is called non-inclusive, if you ever hear that term. So your interval reads from 5 and then stops at 15. So it's all solutions between 5 and 15, non-inclusive. A lot of kids in Algebra 2 look at that and they go, well, how am I supposed to know if that's an ordered pair? Because it looks like an ordered pair. And my answer to that is, because we're not doing ordered pairs. Like, it's context, man. You're doing number line inequalities. I wouldn't be giving you an ordered pair. That's silly. All right, now oars. Who remembers what oars look like? They kick out, don't they? Yeah, like oars on a boat. All right, so x is less than negative 11 would be this away. Or, so this isn't an intersection, it's everything. Or any x's that are greater than or equal to 1. So this time I got a bracket on it and kicking out this way. All right, for all the points in my heart, who's got the interval on this one?
It is negative infinity, comma, negative 11, parenthesis, u,
Well,
bracket, 1, infinity.
Very good. And I know what you meant when you called this a U, but it's really called a union symbol because
What?
Abruzzo gets very angry when you literally draw a U with a tail on it, guys. U with a tail is the letter U. The union symbol is like a horseshoe. Okay?
So do you get points taken off if you?
I will put a big frowny face on your test if you put a U with a tail.
But no.
Because I'm trying to traumatize you enough where you don't go to college and put a U with a tail on it. They will mark you wrong and make fun of you. I will only partially make fun of you in front of the whole class. Okay? Guys, that is a union symbol. Okay? That is a symbol. So you can't change what a symbol looks like in math. It means something, okay? It's challenge accepted. There's going to be tails all over your test. You're going to have U tails, U tail, U tail. Oh my gosh, don't do that. All right, domain and range. You guys remember the concepts of domain and range? Remember hearing them at least?
Yeah.
Heard them before? Anyone want to kind of summarize what domain means to you?
X.
The X's, yes, exactly. What about range?
Y.
Those are the Y's. So the official definition for domain would be the set of all X's for which the function exists, and then the range would be the set of all Y's for which the function exists. Now, domain and range has to be written for us in interval notation. You have to be careful about brackets and parentheses. You have to be careful about the order of the interval. So just to jot down some notes here, the domain represents the X value, which is also the independent variable of my science friends. And then the range, like we were told, represents the Y value, and the Y value is the dependent variable. If you think about that connection to math, like obviously in science it makes lots of sense for independent and dependent, because the independent variable is the thing that you're changing in your experiment, right? Like you're cranking up the temperature each time and you're recording the results. In math, it looks a little weird because we're not really doing anything concrete. You're choosing an X value to plug into the function is what it means. So you choose your X's, plug it into the function. The Y is dependent because it depends on what you just chose for X. That's the idea. All right. Oh boy, I think I might have to pause the video for this one. I have a really dumb metaphor for this one. We'll come back to it in a second. The official definition that they're trying to illustrate to you on this page is whether a set of ordered pairs is a function or not. So any set of ordered pairs is called a relation. And they want to know if we can consider this one to be a function. So set A is the X element, and set B is the Y element. And this is how they're paired up. So like 1, 6 means this is the ordered pair 1, 6. So 2, 8, 3, 8, and 4, 9. And they want to know whether this is a function. Well, spoiler alert, it says right here, it is a function. But then some of you are looking at it going, wait. What about this? There's some weird rule about whether things are functions or not, right? And the rule is every X is paired with one Y. So is every x paired with only one y? Yes. This is a y who's paired with two x's. So that doesn't violate what it means to be a function. So every x has just one output attached to it. I know there's two on one of the outputs, but that's not what the rule says. I'm going to pause the video for a metaphor that I'm going to share with you, but I don't want it on the internet. All right, so every x can only be paired with one y, but the reverse is okay. All right. There we go. This is the visual representation of that same rule, guys. This is the one most kids like the best because it's easier to look at. So the vertical line test is stating that exact same rule. If you draw vertical lines through all of your ordered pairs, notice they're only touching one output value. So all of these vertical lines are the x's, and they only have one output associated with them. But if you have, I'm just going to throw down something that is clearly not a function. You guys cool with me saying that's not a function? Because look at this, look at this, that was supposed to be vertical. Look at this line. This is the same x value. I'm just going to make this up. I'm going to call it x equals 4. And it is producing, or it's paired with, I should say, a y value at, I'm making this up, 3, and also at -3. So 4 is paired with two different y values. See how that's working? So this is a visual representation of saying the same thing. Can we all agree the visual representation is easier to look at? So if you can come up with a graph for your thing, use the vertical line test. It's awesome. Sometimes kids tell me, because I'm going to ask you in the future to prove to me whether something's a function or not, or explain it. And I get kids who say things like, oh, it passes the vertical line test. But they don't graph it. Like, you have to graph it in order to tell me if it passes the vertical line test, okay?
I'm really good with functions, but I can see it in my mind.
You can see the function? Then you're going to take what's in your mind and you're going to transfer it to the paper.
That sucks.
Doesn't it? All right, so this is, I don't know if this is on your paper or not, but this is some extra practice for us, guys. This first one, what do you think? Does it pass or fail the vertical line test? Pass. So this passes, which means, yes, this is a function. All right, what about this guy?
Fail.
Fail. Multiple places, right? Fails, so this is no, not a function. How about this guy down here? Even though it has arrows on the end. That passes, so yes, this is a function. Very good, very good. We'll talk about domain and range in a minute. Now, these, again, these are from your textbook, but these remind me of what's going to be on your homework. So this is one of those XYT tables. So I'll think about my x's being paired up with y's. Is this a function? Is every x paired with only one y?
Yes.
Yes, so yes. Is this a function? No. X equals, is that 4? X equals 4 is one clear example of more than one y value pairing. And then there's this one. Yes, go ahead.
There's a system of functions.
Like a piecewise?
Yeah.
Man, you're good at segues. That's coming up next. All right. What about this guy? Y squared minus 2x equals 5. Now, my friends who like the vertical line test are going to be a bit out of luck because you probably don't know what this looks like. And if you wanted to know what it looks like and if you wanted to graph it, you'd have to solve for y because you'd probably go into your graphing calculator at this point. So you could solve for y. That's what they did here. And turns out, if you were to graph this, you'd have to also remember the plus or minus because we square rooted each side of the equation. When you go to graph this, you end up looking at like something that looks like this. That's the positive version of it, and that's the negative version of it. So right away, you're going to be like, oh, boom, fails the vertical line test. But can we talk about the algebraic piece to it? Because this actually might be a little quicker. We know by definition that if an x value is paired with more than one y, then we're going to have a problem and it's not a function. So can someone give me their favorite number they'd like to plug in right here that would work? 1 sounds wonderful. All right, if I plug in x equals 1, I get 5 plus 2, which is 7, right? And then I get the square root of 7, which is the square root of 7, but then there's a plus or minus in front of it. So that means positive square root of 7 is an output possibility for that, as well as negative square root of 7. So right here, you have one example, one counterexample, if you will, of why this is not a function. X equals 1 is paired up with 2 different y values, and that's a physical representation of it failing the vertical line test. This is an algebraic counterexample, okay? So if you want to use an algebraic method or if you want to graph it, and you get something kind of weird like that, you're going to have to do some algebra so it's in y equals form before you can do any of that work, because your brain only works in y equals form right now. I haven't taught you guys how to do y squareds yet. That's coming up in the conic sections in March. Yes.
If it ever comes out with
A plus or minus.
y is equal to plus or minus.
It's going to fail. Yep. Be careful though. Sometimes they're not square roots. Like if it's a cube root, you don't get a plus or minus on that one, right? Odd roots don't get plus or minuses. Yeah, that's a great question. Did you hear his question? He's like, anytime I end up square rooting it, because it's y squared, it'll have a plus or minus, so I'm just going to assume it's going to fail. Yeah. But my warning to him was, watch out, because if it's cubed, you don't apply plus or minuses to odd roots, do you? So cube root, fifth root. Well, there's a lot of reasons. We're about to learn about symmetry in an upcoming lesson, but the symmetry of it doesn't exist. Like one piece is up here, one piece is down here, as opposed to a parabola looking thing. Yeah, you have opposite solutions. Let's put a pin in that conversation. We got that coming up next, like in another day. All right, so let's, can you guys help me develop something that is and is not a function? Instruct me, child. Give me something that is a function.
Draw a U.
Okay. I'll call it a parabola, but love it. That is totally a function. That's not a thing. All right. How about something that's not a function?
A sideways U.
All right. Well, they're called horizontal parabolas. I know, real fancy, right? I know, that's stupid. Hey, Bob, what do you want to call this? Horizontal parabola? Cool. I know, it's dumb. When we learn the conic sections, you're going to revisit concepts like circles and ellipses. P.S., that is Mrs. Hoffbauer's favorite unit of the whole class. So she's probably going to have 400 worksheets for you to do. Not me, though. No, I'm kidding. Me too. All right, guys, you're at the bottom of worksheet 1 still. And let's explore something that is totally easy for you. What does this want me to do? Plug in -4 into your function, okay? Now, pretend like you're a tutor for an Algebra 2 student. What are they going to mess up? Everything. That's not very nice. What about the negatives? So, if they set this up, I would be very happy as their tutor or teacher. But what do most Algebra 2 kids mess up, at least at the beginning of Algebra 2? It happens right here. They don't use parentheses. I don't know. I mean, you guys know to use parentheses, but apparently they don't. I don't know, I tell them. And when they don't use parentheses and they have something negative being taken to an even power, they're going to lose the factor that this becomes a positive value right here, right? It's not going to affect them here or here, but right here they're going to get a big mistake. This is the old, my calculator gave me the wrong answer excuse. Yeah. So I'm going to show you guys a little bit of you can consider it a shortcut, but you're pre-calc, so I like to show you things like this. Go to your calculator. Go to the home screen. And I'm going to show you what's called storing. So your calculator has a whole alphabet keypad on it, right? You can store variables and letters. You can write messages. That's true. So you can store variables and letters to represent numbers in the home screen. It won't affect how we graph ever. It just, in the home screen, if it thinks x is -4, it thinks x is -4 until you tell it otherwise. So what you do is you type the number first, so -4, and then you hit this stow button down here by the on key, and it pops up a little arrow. And then you can use any letter you want, but I'm lazy, so I always use the quick variable key because it's easy to get to. So you're typing -4 stow x, and then you hit enter. From henceforth, your calculator thinks x is -4 when you're in the home screen. So I can just type the function. I already forgot what it was. Was it 4x to the third? What is, thank you, 4x to the third. What's the rest of it? Plus 6x squared. Okay. And then, was what? Plus 3x. Okay. So a big benefit to knowing how to store variables is you don't have to use extra parentheses, right? Pretty cool. This is a great way to check your answers. If you're like solving an equation sometime in math or on the SAT and you're like, ooh, I don't know if I did this right. Store your answer and plug it back in. Nice, right? It's like your best day ever.
I didn't know what to tell us this earlier.
I actually told you in Algebra 2, but that's okay. Maybe
You weren't in my class.
Yeah,
Well,
I
you might have
did.
said it first semester.
Oh, that's true. I didn't have
I
you
didn't
first.
until
It was a
second
first
semester.
semester thing. That's true. I'm sorry you missed out on that really good experience. But you know now. Hey, can we look at letter B though? Because
Senior year.
finally it all clicks. Letter B is the one I'm a little concerned about, guys, because this is the one that's more pre-calcy. So I'm gonna write the skeleton of it. Your calculator will not help you on this one, guys. So we have to know what this means. And this time they want me to plug in or evaluate the function at 2a. Now, clearly, with a being kept as a variable, I can't type this in my calculator because it thinks a is something else. So don't do that. So talk to me about how I'm going to simplify. Let's start with just this part. Order of operations. Parentheses first, nothing to do. Exponents next. So the 2a has to be raised to the third power. Make sure both of them get raised to the third power. So the 4 can kind of come along for a moment. 2 to the third is what? 8? 8 to the third? Okay, keep going. Let's do a similar thing here on this middle term. The 6 just kind of comes along. But that's a 4a squared. Cool. All right, and then this is a plus 6a. So finally, simplifying those original coefficients, you get a 32 a to the third plus 24a squared plus 6a. There's no more simplification you're going to be able to do on something like this that has an algebraic input. If it's an algebraic input, which it's totally going to be on your test, you just have to suffer through the algebra. Okay? Just be careful.
You can't just divide by 6.
Oh, you want to factor it? You can factor it. I just feel like that's a lot of extra work when I don't want it. Right? You don't want to do that. And you definitely don't want to just divide it out of the problem because it's not an equation. All right. Can you guys move to the back and find this guy? Piecewise! I told you. We were coming back to him. All right, let's see what you remember about piecewise.
Nothing.
Oh, boy. Okay, piecewise. Now, in PreCalc, we're going to see some crazy piecewise functions coming up. We will be graphing them. Not yet. Today, all we're doing is evaluating them. So this particular piecewise has 3 parts. And it says, use this one if your x's are less than or equal to 4. And then it says, use this one if your x's are between 4 and 10. But notice there's no equal to bars on those. So if it's exactly 4 or exactly 10, you got to look elsewhere. And then the last function is this guy. Use this if your x's are greater than or equal to 10. So this first question says, I'm supposed to plug in x equals 1. So that falls under the less than 4 category, right? So go ahead and plug in 1. You get square root of 1 plus 1, better known as 1 plus 1, which is dose. And then what if I want to plug in x equals 3? Well, that's the same function still, right? We're still less than 4. So this is weird because square root of 3 plus a 1 is something gross. So I'm just going to write square root of 3 plus 1 because I'm too lazy to grab my calculator. What about if I equal 6? What if x is 6? That falls under this middle category, right? So you plug it into 3 times x. So we're going to get an 18. And then you know the last one's going to be the green one, but let's see why. If x is exactly 10, it says right here, if you're greater than or equal to 10, use this green one. So plugging in a 10 here, it's 200 minus 15, which is 185. Thank you. So evaluating piecewise is as far as we're going to take it today for piecewise functions. We will be graphing, but save that for next week. Or after. It's actually after next week. All right. The one with stars on it. That looks promising. Let's do that one. Okay, x plus 8. I want to evaluate this function at the expression x plus 8. This is a question that's practically pulled off of your test next week. So let's take a look. Think like a tutor. Think like a teacher. What's going to go wrong here for some kids if they're not careful? This very first part right here, guys. X plus 8 squared means...
X squared plus 69.
Not that. You got to FOIL it, right? So this is x squared plus 16x plus 64. And then here, be careful you're distributing a negative 8, so that's minus 8x minus 64. And then don't forget that you have a plus 1 on the end. So of course, your algebra teacher, pre-calc teacher, all of us want you to simplify. The 64s knock each other out. And you can collect your like terms here. So you end up with something that's really quite close to the original. That is kind of coincidental that it worked out this way. So don't think it's always going to work out that way as coincidence. There's one just like that on your test next week. All right. I'm running out a little bit of time here, guys. Can we talk about these questions? Domain and range in interval notation. So if you're a little rough on domain and range, please write these notes to yourself. Domain, you guys told me earlier were your X's, and you have to read them least to greatest. So you read domain left to right. Range, you guys told me were your Y's, and you have to read them bottom to top. And you also have to be careful about brackets and parentheses. So the domain of this function starts yonder, which is at -4, but do you notice something kind of weird about that point? Do you see how it has an open circle? So you can't tell me a bracket, you're going to tell me a parenthesis. So it starts at -4, but not really. And then how far to the right does this stretch? I think forever. There's an arrow there, huh? So infinity. Okay, so domain goes from -4 and then goes forever to the right. What about range? Range is how low it starts. I think it's -1, but yeah. And again, it's an open circle, so -1. And then how high will it go? Infinity. Very good. And then everybody's favorite, the one that has arrows on both ends. What's the domain of something that looks like this? Yeah, it goes forever. So -infinity to infinity. But guys, that's not the case for range. Where does your range begin? Starts at 0 and then it does go up forever. Now, because there's an actual point here, it's not an open circle, I want you to use a bracket to start off your range at 0. Remember doing these? A whole lot of these. All right, let's do a funky one. Let's do number 9. Domain, the leftmost starting point here, guys. Where does it start? I'm on number 9 here. So -3 with a parenthesis, though, right? Because there's an open circle. That's weird. And then how far to the right will it go?
3.
Yeah, 3. Now, notice, there's no open circle anymore. There's an actual point. So you need to bracket that one off. That's weird. And then range starts down here at -2 with a parenthesis. But it stops up here at 3 again with a parenthesis. So watch your endpoints. PreCalc, we get kind of crazy with endpoints. So. All right, for your homework, you can only do part of your homework. So maybe on your homework check, circle those questions for me, okay? We got to finish up this lesson tomorrow. Those are the questions that are circled. Those are the ones you can actually do right now. Remember, it's in your textbook. We will be posting a PDF. If she hasn't already, it'll come soon. All right, good luck.